Today, I would like to be talking about the unification of inflaton and dark matter by an axion-like particle. So this talk is based on the two papers in collaboration with Ryuji and Fumi, and an ongoing project in collaboration with Fumi. So, introduction. As you know, the success of the lambda CDM model relies on the two unknown degrees of freedom, the inflaton and the dark matter. Interestingly, they are similar. The inflaton has a very flat potential to drive the slow law inflation. This implies that the inflaton is very likely to be a neutral field. So that the Coleman-Weinberg correction to the potential is highly suppressed. After the slow law, this inflaton starts to oscillate around potential minimum, so the coherent oscillation energy dominates the universe once. Then, due to the decay to some of the particles, the inflaton reheats the universe. During the slow law, there is quantum fluctuation on the inflaton field. This quantum fluctuation or quantum diffusion later becomes the density perturbation of the coherent oscillating inflaton. Through the decay, this perturbation becomes the dense perturbation or primordial dense perturbation of the plasma, thermal plasma, including the photons, including the baryons. On the other hand, the dark matter is also neutral because they exist today around us, but we cannot see them. The dark matter is also known to be cold and long-lived. Interestingly, we now know that dark matter has a suppressed isocurvature mode. So the fluctuation of the dark matter density looks quite similar to the perturbation of that of the photons and baryons, which originates from the fluctuation or density perturbation of the inflaton field. Therefore, the inflaton and dark matter are quite similar. They are both neutral particles or fields, and ones dominate the early universe and have similar density fluctuation. The main difference between the two is that inflaton decays, but dark matter rarely decays. I will not explain in detail, but the history or energy history of the inflationary cosmology looks something like this. So once inflaton dominates the universe and dark matter also dominates the universe. A very popular question in this sum of history or cosmic history is the origin of the dark matter. So when and how the dark matter are produced. In fact, there is an interesting possibility or simple possibility is that the dark matter is the inflaton itself. So it is not produced, but it just remains. In this case, the reheating due to the inflaton decay to some particles is incomplete. So some fraction of the inflaton energy condensate oscillation coherent oscillating condensate becomes the dark matter, becomes cold dark matter. So this is a simple possibility, but if we consider this, we have to answer the question why the inflaton is long-lived in the vacuum. There are several possibilities. One possibility is that the vacuum has a symmetry of this inflaton. So, like the wind, this inflaton is lightest charged particle under this symmetry. Therefore, in today's vacuum, this inflaton can be stable. But in the early universe, during the inflation, this inflaton field is deviated from the minimum value. So or the bed, then the inflaton can be hit the universe. More recently, it was considered this symmetry can be approximated due to the quantum gravity effect. Then the parameter region will become very different from the previous study. Today, I would like to focus on another possibility, that is the slow law condition to suppress the decay rate of the inflaton in axion inflation. This is what I will be talking about. I will show that in a large class of axion inflation models, the inflaton can be the dark matter whose stability is due to the slow law condition. By coupling the axion to photons, then the axion becomes axion-like particle or arch. Then we have successful reheating due to the coupling. Interestingly, the dark matter abundance can be explained due to the incomplete reheating in the parameter region of in the mass and the coupling to photon problem like this. This is interesting parameter region because it can be tested in the future axion helioscope, YAX or TASTE, and also it is hinted in various astrophysics phenomena, like the horizontal branch star cooling. Lastly, I would like to comment a little bit on our ongoing project about the ARP coupled to gluon, and I will discuss the strong CP problem. Well, let's discuss in detail. So I want to talk about axion inflation. The reason is that if we consider axion inflation, the dangerous lattice correction are naturally suppressed due to a discrete shift symmetry. We need to suppress the lattice correction to guarantee the slow low condition. So the discrete shift symmetry looks like this. Then the potential becomes periodic. So we can expand the potential in Fourier series. There are various realizations of axion inflation. The famous one may be the natural inflation. In this case, the potential has a single cosine term. However, it is known that if we want to explain the CME normalization and the spectral index, then we need a super Planckian decay constant for this model, and a super Planckian field excursion for inflation. In addition, very recently, this model is excluded because it predicts to large tensor to scalar mode. So basically, the reason is that the inflation scale is too high. So we are led to consider the axion potential with two or more cosine terms. In this case, the model is called multinatural inflation. In multinatural inflation, the CMB data can be well explained with sub-Planckian decay constant and the sub-Planckian field excursion. For simplicity, let's consider the cosine, the potential composed of the two cosine terms. In this case, with an additional cosine term, we have additional parameters. Let me explain this. So the capital lambda is the inflation scale. The theta is the relative phase between the two cosine terms. We can always eliminate one of the phase in the cosine term by field definition. Then this is the generic phase in this setup. But anyway, so this is a relative phase. Kappa is the relative height between the two cosine terms. And here n is an integer characterizing the second cosine term. In today's talk, I would like to focus on this n is odd integer. So this is actually an important assumption to derive the result. So we take this n to be odd. More precisely, I will take this to be 3 to discussing some figures, some results. But anyway, so let's consider the kappa around n is odd and kappa around 1 and theta around 0. Then the potential looks like this. You can see that there is a flat hilltop in the potential. In the limit kappa to 1, theta to 0, we can find that the Taylor series around the origin has a dominant quartic interaction. So this quartic term can drive a quartic hilltop inflation in this limit. Then it is well known that the quartic coupling is fixed to be around 10 to 12 by the CME normalization. This condition also fixes the ratio of the inflation scale to the decay constant in our model. It is also known that the quartic hilltop inflation cannot have a consistent spectral index when the inflation scale is not that high. But in our model, we can have a relative phase which contributes to the linear term in the Taylor series. Thanks to this linear term, we can slightly shift the horizon exit of the inflaton field. In this case, we can slightly change the curvature at the horizon exit so that we can enhance the spectral index. So we can get better fit and consistent or successful inflation consistent with the CMB data thanks to this linear term. By introducing this linear term, we have also slightly modified the curvature at the hilltop. In particular, with this linear term, the hilltop will have a curvature around the Hubble parameter square. So, this Hubble parameter during inflation is a typical energy scale or renormalization scale during the inflation. But anyway, so then you will have the curvature of this value. The interesting feature in this model is the upside down symmetry. This is because we take n is odd. As long as n is odd, we have this this symmetry. And also in some other extension of the model, we will have this kind of symmetry. You know, in the original natural inflation, we have the upside down symmetry. But anyway, so if we have this upside down symmetry, the interesting thing is that the property at the hilltop is linked to the property in the bottom or in the vacuum. This means that the normalization, the CMB normalization, predicts that the self-coupling or chaotic coupling in the vacuum is around 10 to 12. In addition, the curvature at the hilltop means that the mass at the in the vacuum is around the Hubble parameter. Then we can massage those relations and to obtain the relation between the mass and decay constant. So this is an interesting prediction in our scenario. Now let's consider this axion coupled to photon. Then we can call this axion-like particle. Then the parameter region is like this. So horizontal axis is the axion mass. The vertical axis is the photon coupling. So this solid line is the prediction. So with the C gamma equal 1, and this one is C gamma 0.1, which, you know, this C gamma is the anomaly coefficient. So it is naturally order 1 or maybe 0.1, depending on how the electric symmetry is broken. But anyway, so this is a natural region. But on the other hand, this colored region are excluded due to the observation of astrophysics and CMB. Well, you can see that the success of inflation predicts the region here, which is consistent with the various bounds. The important thing is that in this region, the sub-electron volt or electron volt scale arc can be the dark matter because lifetime is, you know, much longer than the age of the universe. So let's talk about reheating. Since the arc coupled to photon, it naturally reheats the universe. You know, I mentioned that the arc is stable in the vacuum, but it is not stable in the early universe because of the large chaotic coupling, thanks to the upside down symmetry. Due to this large chaotic coupling, at the onset of oscillation of the inflaton, you know, we have large effective mass because, you know, the amplitude is large. The amplitude is around the decay constant at the onset of oscillation. Then, by considering the decay constant around 10 to 7 GeV, then we can find that effective mass is around 10 GeV. This 10 GeV, you know, is 10 order of magnitude larger than the vacuum mass. So this enhancement means that the decay rate at the reheating or at the onset of oscillation is around 30 order of magnitude larger than that in the vacuum. So the inflaton can efficiently decay into the pair of photon. Strictly speaking, it is too efficient. It produces too much photons, and the photons soon form thermal plasma, and there is thermal blocking for the inflaton. Later, this inflaton cannot decay into photon due to the thermal blocking or thermal effect. Instead, the inflaton can scatter with the plasma to evaporate, to dissipate energy into the thermal plasma. Well, by taking into account of the decay process and the dissipation process, we have solved the Boltzmann equation to check whether the reheating is successful. In addition, we have checked the remnant of the inflaton because it will become the dark matter. The remnant becomes dark matter. You know, it must remain because, you know, the dissipation and the decay rate are both related to the effective mass. So effective mass is relevant to the amplitude, and if the reheating is efficient, amplitude decrease, which means the decay rate and dissipation rate are suppressed. So it must remain. So by imposing the remnant of the axial abundance to be the dark matter abundance, we have the parameter region like this. Here, the colored data points are the natural points, right? I mean, the anomaly coefficients are order 1 or 0.1 or so. So those are natural points. So we can see that the natural point to explain the dark matter abundance are consistent with the cast bound and the horizontal branches are cooling bounds. More strictly speaking, we need to be more careful because you know, the reheating is via the dissipation effect or scattering. So this is basically a thermalization process. Then we have to also care the back reaction, which produced ALP. So this is also thermal scattering process, which have a very, you know, similar diagram. So if the reheating is efficient, the thermal production is efficient. Some amount, so the ALP particles are thermalized. So in our universe, in this case, we have two kinds of components. The first component is the ALP condensate, which composes of the low momentum mode of the dark matter. On the other hand, we also have a hot component because this from the thermal production. This hot ALP is characterized by the effective number of the neutrino around 0.03. We need to have this hot ALP abundance small enough. Otherwise, the dark matter would be free stream. This set up mass bound of ALP to be smaller than 1 electron volt. This comes here. So we can see that successful inflation, dark matter abundance, and hot dark matter bound are consistent going to here. In addition, there is also another bound from the requirement for the ALP condensate. I didn't discuss this in detail in today's talk, but our ALP condensate is later forming dark matter, so we need the form of dark matter early enough to have successful galaxy formation. So then the ALP mass should be higher than certain value. So basically, we can find that those independent conditions point to this region. We consider this coincidence quite non-trivial, so we call this region or this scenario ALP miracle. In this region, you can see, large portion of this region overlap with the future reach of the Yakuzo. So basically, most of the parameter region can be tested in the Yakuzo. In addition, since this scenario predicts the dark radiation, so basically this dark radiation can be proved in the future CMB and the BAO experiments. Also, the interesting thing is that this kind of region is hinted in generic sense for the ALP. For instance, there is a hint from the horizontal branches that cooling, and there is also a hint from the extragalactic background light analysis. So I think this is an interesting region. So actually, this is the end of the main part about ALP miracle. In the next, I would like to talk about slight extension of this scenario. So let's look into this figure again, and we can also see another coincidence. That is the coincidence between the QC reaction region and the ALP miracle region. I think it is a natural question to ask whether this ALP the one solving the strong CP problem. Naively, it is difficult because the supernova bound and the neutron star cooling bounds, they set the decay constant to be greater than 10 to 8 or 10 to 9 GeV. On the other hand, the ALP miracle lives at the place with a decay constant around 10 to 7 GeV. So it's basically, if we have a gluon coupling to be relevant to the strong CP problem, then basically it is excluded due to the star cooling. But in the next, let's take this coincidence seriously, and let's consider whether really this ALP cannot couple to gluon. In fact, it can couple to gluon without spoiling the consistency with the star cooling. This is the so-called hydrophobic or nucleophobic axiom. For simplicity, let's consider this kind of Lagrangian, this ALP coupled to uptight quark and downtime quark. If this coupling CU and CD are generic, then the ALP have a gluon anomaly. So basically, it couples to gluon. When we take CUMU equal to CDMD, there's an interesting feature. We can see that this ALP is almost isosinglet. So the ALP pion mixing is suppressed. On the other hand, if you take MU to 0, MD to 0, we can see this ALP completely decoupled from the system without mixing. Then, this means that ALP only, in this Lagrangian, only coupled to the nucleon with a small correction of the iso symmetry breaking or chiral symmetry breaking. Therefore, we can suppress the ALP coupling to the neutron and the proton. This relation is not very difficult to satisfy because MU, the ratio of MU to MD is around 0.5. So we can just take this CU equal 2 or CD equal 1 also. Then we can get this kind of the suppressed coupling. And those coupling are consistent with 0 by taking into account of the hadronic uncertainty. If we take the central value of those coupling, we can find that the supernova bound neutron star cooling bonds are relaxed to be around decay constant around 10 to 7 GeV or so. Then we can open the region for the Alp miracle with coupling to Guru. Let's consider that inflaton has this kind of charge assignment. Immediately, then we have to consider the correction to the inflaton potential, because once we couple the axion to QCD, then we have the gluon, then we have this kind of instanton effect. The problem of this effect is that it breaks upside down symmetry by using this concrete form. The breaking of the upside down symmetry does not spoil the successful inflation. We can still have the successful inflation, because we can in the expansion after the hilltop, the Taylor series of the hilltop, we can have certain parameter redefinition like this. Then everything does not change, so we can have the successful inflation as well. But then the upside down symmetry breaking corrects the Alp mass. The interesting thing is that when we take this theta QCD, which is the phase, the well-known phase in the QCD sector, to be 0, then the prediction does not change much. Still, we have the M phi around the Hubble parameter. This is because of the coincidence of the QCD action region and the Alp miracle region. This when theta QCD is 0, then at most this contribution gives the mass around the QCD action mass, and the QCD action mass is around the Alp miracle mass range due to the coincidence. Therefore, at the most, it corrects the mass Hubble parameter relation by order 1. However, when the theta QCD is not that small, then we have to be careful, because this term induces an upside down breaking linear term, and we have a large self-coupling from the upside down symmetry. Then this linear term shift the vacuum from the upside down symmetric place, or from the pi f phi also. Then due to the large self-coupling, there is a large curvature. So with not very small theta QCD, we will have a large inflaton mass in the vacuum. Note that we cannot have very large mass because of the dark matter bound. So by considering the hot dark matter bound, we must require that the mass to be smaller than 1 electron volt also. Then this means that the strong CP phase should be smaller than 10 to minus 9. In other words, requiring the Alp coupled to gluon and requiring the consistent dark matter physics and inflation physics, we predict that the strong CP phase to be smaller than 10 to minus 9. Although I don't have time to explain in detail, but now the Alp can couple to gluon, then we can consider the gut setup for the axion coupling. Interestingly, the hydrophobic axion can naturally originate from the SU5 cross U1 PQ. Then the parameter region is like this. The gray data points are excluded due to too large strong CP phase, but most of the data points are consistent with the strong CP phase. So yeah, basically the prediction in the sub-electron volt range has a naturally suppressed strong CP phase. Well, this is the end of my talk. Thank you very much.